You get a week one here, and I'll post the link to the YouTube recording here. I'll also post the lecture notes and slides. I was debating this semester whether to do PowerPoint or just handwritten notes. And so after talking to some people, I decided just to do PowerPoint. And so that could change. So I didn't post the PowerPoints until last night. And so you might have missed this depending on when you access Canvas last. But it would be here. So the textbook PowerPoint slides, these are straight from the book. So I haven't modified these for my lecture. I haven't been using these because I just have the material organized differently than the book for many of these chapters. But I'll use these and just show you how it relates to how I have the material organized. Okay, let's take a look at the syllabus here, and then I'm going to go through the course information and the schedule of the syllabus. So you can download these if you like, or just open the page. I'll just open this. I downloaded this, so I'm going to use Acrobat to take a look at this page here. All right, if you're going to be absent the first week, make sure you send me an email or leave me a voicemail. Otherwise, I don't know if you decided to drop. You know, one of those people who said, okay, this class is not what I was looking for. That way I won't drop you. And so this is especially critical at the beginning of the semester when there are people trying to add. And each time there's an absence, a lot of people are thinking, okay, that's a spot that's opening up for me. But if you're just absent, like you're sick or something, or you have an appointment or something else, let me know. The office hours I'm going to start tomorrow. I have, well, today I have this extended office hour after class. Our class ends at 4:25. I go to 6:15. I have a morning lecture that ends at 12:55. So I'm in this room at 12:55 to 1:15. So if question comes up, you can always find me here at that time. And then after class, I'll stick around to answer any questions, but I'm not going to stay until 6:15 because I think we haven't really covered that much material quite yet. And then I have an office hour tonight, which is going to be online from 9:30 to 10:30. I used to have these via Zoom, but there's something wrong with Zoom right now. And then I switched to WebEx, and now there's something wrong with WebEx, and now they have another one that they're using for online office hours and lectures. So I'll post a link in Canvas for the online office hour. You can pop in between 9:30 and 10:30 p.m., but this will be starting next week. Tomorrow we'll start our regular office hours with Tuesday 12:55 to 1:15. This is after my morning class, and then after this class 5:40 to 6:30, which is a bit extended. And then on Wednesdays from 12:50 to 1:10 and 4:20 to 4:40. Essentially, we meet 3 hours per day. A little over 3 hours per day on Mondays and Tuesdays. Tuesdays are lab days. And on Wednesdays, it's 5 minutes shorter. So we get out, rather than 4:45, we get out 4:40. Okay. Okay, if you haven't had any chem before, let's talk about the field of chemistry. And take a look at the dictionary definition here. I like number 2, but I would like to modify this a little bit here. If I could modify this, I would probably change a little bit of the wording. Number 2, the composition That is what it's made out of. Structure, properties, and reactions of a substance. One of the first things I changed is substance. We have a very precise definition of what a substance is. And chemists study more than just substances. We have things called mixtures too. And so we have substances and mixtures. Do you know the difference between a substance and a mixture? A substance would be like water, like pure water. A mixture would be like lemonade. There's more stuff in there. And lemonade is made up of a whole bunch of different substances.
So like a mixture has different types of molecules?
Different types of molecules, whereas a substance would only have one type of molecule, and that would be it. So that would be one way. We'll talk about what molecules are shortly. One of the things that differs between a substance and mixture are some of the properties. So if you have sugar water, does all sugar water taste the same? Exactly the same? Is some sugar water sweeter than other sugar water? Yeah, it depends on who mixed it up. It's like lemonade. Does all lemonade taste exactly the same? No, so mixtures have variable properties because you can change the composition. If you change the composition, it'll change some of the properties. Those properties depend on how much sugar you have in there, how much water. Whereas a substance, it doesn't change. Like water, does pure water taste different than pure water? Like say pure water here in California tastes different than pure water in New York? If it's pure, no. But tap water, yes, because tap water is a mixture, and mixtures depend on what's inside there and what its composition is. So that's one of the distinctions. So we don't just study pure substances. Yes, of course, it would be nice to always study pure substances, but some things aren't pure substances, like sugar water. And so we study mixtures as well. So rather than substance, let's try to have something a little bit broader that would encompass things like mixtures. And so can you think of something that would be short and would encompass mixtures and substances together? You would think there'd be a simple word, and maybe it is, but this may be going quite broad. And so rather than writing substances, I'm going to say that chemistry is the composition, structure, properties, and reactions of matter. Have you heard matter before? Matter, what is matter? Now, matter has a definition as well. There are some things that are matter, and there are other things that aren't matter. And so what things is like sugar water matter? Yes. Is pure water matter? Yes. Is wood matter? Yes. Is air matter? Yes. And so there are lots of things that are matter. In fact, you know what matter is? Matter is the physical material of the universe. So, the universe is made up of matter. And what the chemists study? They study matter. And, okay, so if that's matter, the physical material of the universe, then what is not matter?
Psychological thoughts.
Thoughts? Yeah. Thoughts wouldn't be. So chemists, that's outside the realm of chemistry. So
Would light be not matter?
Life? Light? Okay. Is light matter? Light, turns out, is not matter. Light is not matter, but it's a little bit tricky because we need something even broader than matter. But it's okay. We're going to leave this as matter because light doesn't constitute matter, because the way matter is defined is this. Matter is anything that occupies space and has mass. And the problem with light is it doesn't have mass. You can't like bottle. Can you put light in a bottle and then take it with you? Well, you could take a flashlight with you, but it's not capturing the light. The flashlight is, yeah. So light is not matter, but do you know chemists study light? You know why chemists study light? Because light interacts with matter. Otherwise, let's see. If this room were pitch black, could you see this table, which is also black? Maybe not, but does it still exist? Yeah, it does. But so we look at how light interacts with matter. The table's still there. It's matter. We're going to study it. But light is not matter, but since it can interact with matter, we're still going to study light, even though it doesn't classify as matter, but we're interested in matter. And light can, change some of the properties. Some things change color depending on what angle the light hits it at, and that type of stuff. And those things are interesting for chemists. What else is not matter that it turns out chemists study? And this is related to light. When we think about light, what is light? Well, light turns out to be energy. Light is energy. Light can power solar cells, like in my calculator. My calculator and my watch. I have a watch. My watch is solar powered, but if I wear long sleeve, then my watch dies quite frequently. So, thinking it really needs light, and so sometimes I have to put my watch outside and let it recharge. It's a fairly new battery. I thought it was the battery, but it just doesn't have much capacity. But light is energy. Is there other forms of energy? And it turns out there are other forms of energy. And energy is not considered matter because can you box up energy and then weigh it and then give it to somebody? Here's a box of energy. I'd like that because I need energy. But no. You could, in a certain sense, you could box up energy. Like if you have an energy bar or energy drink or something like that, but it's different because it's not energy. It's something that has potential to be converted into energy, like a battery. A battery is not a can of energy. It's something that has the potential to create energy or to make energy. All right, so I would change this to the composition, structure, properties, and reactions of matter. And we're interested in matter. What is matter? Matter is the material of the universe. That's what things are made out of. And so this is why people say chemistry is the central science. People say that chemistry is the central science because chemists study everything. Everything's made of matter, so that's what chemists are interested in. The other thing I would change is this. The way chemists define properties is different here. There are two types of properties that chemists are interested in. You might have heard them before. One type of property are the physical properties. Things that are physical properties would be like color, form. The form would be, is it solid, liquid, gas? Color, form. Can you think of any other physical properties of matter? Density would be another physical property. Melting point, boiling point, etc. They're laws. And so we have one category of properties called physical properties, and we have another category of properties called chemical properties. And so what are the chemical properties? The chemical properties are reactions here. And so in this acronym just says properties. And so when people think properties, when chemists think properties, they think both physical and chemical. So if somebody says properties, then there's a list of physical properties, and then there's going to be a list of chemical properties. Can you think of a chemical property that we might be interested in?
Whether it's an acid or a base.
Yeah, whether it's an acid or a base. We'll talk about acids and bases later. Acids and bases are important in the biological system of your body. Like, for example, your blood acidity or basicity can be measured by pH. And if your blood becomes too acidic or too basic, it can be potentially toxic. And your blood pH has to be maintained within a very narrow range. Your blood pH is like 7.2. And so if your blood pH goes from 7.2 to 7.1 or 7.0, that's big trouble. Or 7.3, 7.4, something like that, as I recall. Is it 7.2? Biology? People for blood pH? So blood pH is 7.2. Do you know what pH 7 is? What pH 7 is neutral. Some people don't like pH 7, like water. Some people like higher pH water. Have you seen that? Yeah. It gives it slightly different properties. The higher pH gives it a more slipperier texture. And, and so acidity or basicity, that is, what types of reactions would it undergo? And it can react with acids or bases. Can you think of another type of reaction or chemical property? Oxidizing, yeah. Like rust, iron rusting is an example of that. Or oxidation could be more extreme. Like iron can oxidize so quickly it can catch on fire. Have you ever seen iron catch on fire? Iron, it depends on the size, but it's easy to catch iron on fire if you have it in the form of steel wool.
You probably know Vistaprint for business cards. Yeah, we print that. But did you know we also print that?
We needed some way of lighting the steel wool on fire. At first we tried using 2 wires and an outlet. That wasn't a good idea. Oops. So we decided to just use a 9-volt battery instead. The steel wool doesn't burn very well when it's bunched together, so we need to fluff it up to make it burn faster. Blowing air onto the steel wool increases the amount of oxygen in contact with the steel wool and makes it burn faster. This is the effect we're going to use later on in this video. And now, let's put on some gear.
That with physical properties, chemical identity, that is the substances it's made out of, doesn't change. So if you have, let's say, a chemical property like boiling or freezing, it's still water. And so if you melt ice and convert that into liquid water, or you reverse that and you liquid water and convert it into ice, it's still water. Whereas in a chemical reaction, its identity changes. And so it's no longer going to be water. And so that would be the difference there. All right, so if we change that, then that would be a pretty good definition there. And then definition 1 is very similar. The science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. There. But again, it's a similar situation. This one's a little bit more broad, because atomic and molecular systems is what matter is made up of. They're made up of tiny particles called atoms or molecules, but there are more different types of structures in there, which we'll talk about later. All right, so when we study matter, then we're going to be looking at these different properties of matter. So this course introduces the principles of chemistry, modern concepts of atomic structure, and periodicity as a basis for understanding bonding. And so bonding deals with how the particles are attached to one another. Chemical formulas, the composition, chemical equations, the reactions, and chemical reactions, also reactions. The equations could be processes like melting, or we'll talk about those. So this is a little bit, to be cleaned up a little bit too. States of matter, important elements in their compounds, solutions, acid-base theories and reactions, net ion equations, oxidation reduction, kinetics, and chemical equilibrium, chemical nomenclature and calculations. In the laboratory, emphasis is on observations, measurements, elementary quantitative experiments with an introduction to qualitative analysis. So that's the class in a nutshell. And we'll be looking at these in much greater detail as we go on. And so this would be the course objective here. You can read through that. We have student learning outcomes. We just have 2 of these here. There should be a lot more, but this was the minimum required. And basically, you want to master all these concepts here. All right, the required materials, we'll need the textbook. The textbook, you could either get the 6th or the 7th edition. I only have the 6th edition, and I asked the publisher for the 7th edition. I never got it, so I finally broke down. This was last year, and bought it. And so the PowerPoints I have posted there are from the 6th edition, because that's what they gave me. And the homework assignments from the 6th edition. But there was a small change with the 7th edition. They added a general interest section right at the beginning of the chapter. And so the homework is slightly different for the 7th. But I broke down and bought the book. The book is over $300. It's an expensive book. But you can buy the online version. It's a lot cheaper. I have the print version here. So I'm going to update the homework coming up. And so just be aware of that. The 7th edition homework assignment might change a little bit. All right, the book is really expensive, but this is not. This is cheap. And this is the Chemistry 4 Supplement and Laboratory Manual. So if you find this one online and you printed it out, it'd cost you more to print it out than just to buy it from the bookstore. Or charging you less. And so this you'll need for laboratory. 3, a non-programmable scientific calculator. If you haven't purchased one yet, get the one that's one step above the basic one. So the basic one's like a $10 calculator. The next level would be like a $15 calculator. And the next level is going to have a little bit more functionality. So let's take a look at the one I bought. I got this one off Target. Website. It was $15, but it's on sale, I think. The student just asked me if this is the one. I think this is on sale now on Amazon. No. There's one seller that's selling it for less than $15. I think the normal retail price now is $25. But what this has is it has a equation solving. This equation solver. And this will save you a lot of time if you're planning to continue on to Chem 1B. In Chem 1B, you have to solve the quadratic equation. Solving the quadratic equation by hand is time consuming. And if you can just solve it by punching it in the calculator, so you have time to work on other problems and tests. So get this. If you don't have it, you can solve the quadratic by hand. It's not that big of a deal, but this is a pretty nice calculator. Texas Instruments also has one that has an equation solver built in. Just anything with a solver, but it can't be programmable. So this is a non-programmable calculator with equation solver. And so this is the one I have. It's pretty good.
What are you going to be using the textbook?
Are you going to be using the textbook?
Like, how are you going to be using it? How are you going to, I mean, this textbook, yes, is $300, so you can, this is why I put the 6th edition here. You can find the 6th edition for pretty cheap online. But I always like to buy the textbook for the course, and I like to buy the physical one. I don't like to buy the electronic version because eventually you'll lose it. I like to have it as a reference for future classes. So if I'm taking Chem 1A, it's nice to have the Chem 4 textbook to go back and look at certain topics just to get the basics down. But during Chem 4, it depends on how you study. When I was a student, a lot of professors gave study tips, and one of the study tips was to read the book before lecture. So I tried that, but it took too much time. I didn't have enough time to read the chapter before coming in, and so it would be like today. You see, I'm covering chapters 1, and I'm going to start chapter 2, so you read chapter 1 and 2 in the book. But I tried that and gave up. I don't do it that way. What I do is how I use the book, and you could use it any way you want, but the way I use the book is I go to lecture and I see what the instructor says is important. And then the stuff that I'm confused about, that's what I really read. You know, there's some study tips that say read the chapter 5 times. I've never read the whole chapter 5 times, but I would read one section like 5 times over and over again until it clicks, you know. And so anything that seems fairly simple and straightforward, I'd skim through in the textbook. Anything that seems difficult and complicated, I'd slow down and read those carefully in the textbook. And it's just to supplement the lecture. And so in the lecture, oftentimes I didn't understand certain things, and then I'd go to the book and look at trying to gain an understanding from that. But sometimes the book wasn't enough, and so I'd look for other books. And this is another tip I have down here. And so we have this room over here, which is Chem 106. This is student study room. In the student study room, there are other textbooks available there that you can look at to get some additional, you know, one author might explain a topic this way, another author might explain it a different way using different examples. And so that might be helpful.
So do you think we would be still able to succeed in this course without having to purchase the book, or do you find like it's pretty important?
All right, so could you still succeed in the class without having to purchase the book? Yes, that's possible. You could succeed. You would have to get the homework though from somebody. That is, I think there's a copy of this book on reserve in the library. There's supposed to be a copy on reserve in the library, so you have to carry it around. And so you have to take the homework from there to do that. If you understand the lecture material, you should be all right. But like I said, sometimes if you get out of a lecture, you don't understand what's going on. That's where the book really helps to go into things in more depth. Sometimes the book doesn't go into enough depth, so I use like if I were in Chem 4, I'd use the Chem 1A book to try to understand it, because in the Chem 1A book, they might devote the whole section on something in the Chem 4 book that they devote one paragraph to. So we'll expand on it. You don't have to know it in that much depth, but you know, it helps to better understand the topic. It's a good book. Books have gone up a lot in price. You know. When I was a student, I had never really thought much about the price of the book. The price of the book, I was looking at one of my books, it was like $25, brand new. But now I look at the price, how, you know, obviously that was many decades ago, but the price is skyrocketing.
For $50 for the 7th edition.
For the 7th edition? Yeah. Oh, good deal. It's a great deal. Sometimes it's bundled with OWL. OWL is their online package that they have, but we aren't going to be using OWL, so you don't have to purchase the book with OWL. You can get it anywhere. And so, even the 5th edition, the difference between the 5th and the 6th edition is nothing. You can get by with the 5th edition. You know. I have the 7th edition PDF. If anyone needs it, I can give it to them. All right. Yeah, that's nice, but I have to say no comment on that one because the publisher. Yeah, you could do whatever you want. I'm not going to police anything. The same thing with the supplement. I don't care if you buy it in the bookstore, personally. There are lots of PDFs of this floating around. It's just if you print the whole thing. You don't have to print the whole thing. You just need to print the report sheet. That's fine. But there are lots of PDF copies of the supplement. If you have an older edition of the supplement, it's not a problem. The latest edition is the 2019 version. If you have that, then it's the same as what I have. If you have the 7th edition, then you have a newer edition than me. Online, I only have access to the 6th edition. I can't understand why, but it's all right. This is for lab. For lecture, you could use whatever notebook you want, but for lab, it has to serve as a permanent documentation. So there's a permanent documentation of the lab data, then we need a permanent binding. So the permanent binding would be a sewn binding, not spiral bound, not these tear out sheets. The pages have to be sewn into the binding. That way, if you tear out a sheet, it's easy to tell somebody tore out a sheet. Because the lab data, lab notebooks, all these, they have to meet a certain legal standard, especially if we work for some private company, who discovered that, or, who has rights to this, that kind of stuff pops up. And so they treat the lab data.
So if you have one already, do you have to get a new one?
What's your lab notebook? If you have one already, no, you don't have to get a new one. You have one with sewn binding?
Yeah, like the normal composition.
Yeah, if you have a normal composition book, then you can use, we're only going to use 20 pages or something, 30 pages. So you just have a line, table of contents, number the pages, so you can figure it out. In fact, so you don't have to buy a new one, but it has to be a sewn binding. Don't tear out the other class though. Leave all the pages in there. You'll need safety goggles. If they run out of the graph paper, the quad roll version, you can get by with the college roll combo. These are the visor gogs here. These are the only ones that are available at the bookstore. If you're on a budget, we do have a lot of used pairs that you can use, or you can even have. I don't know how many we have left, but when COVID hit, we shut down the labs, and there were a lot of goggles that we kept them, expecting them to be reclaimed, but they were never reclaimed. And so they just went into surplus. Didn't throw them away, so people can get a pair. But these are different than, let's say, shop glasses. The shop glasses often have ventilation holes. We need splash and impact protection. And so the splash protection, so if you have ones with ventilation holes there, they probably aren't going to be acceptable. You need a proper seal, around your bridge of the nose and your cheekbone, cheeks, so that if you get a splash up, it won't get into your eyes. These are okay. These offer splash protection, and these fit over glasses. There's not, you think there's a big gap on the side here, but there's very few splashes that come in horizontally from the side. Most of them will come up from the bench. And so those are the visor gogs. I think they're $15 last time. That's required. We are going to need the goggles for tomorrow's lab, which I'll talk about in a minute when we get to the schedule. Some optional stuff. Sharpie is nice for labeling glassware. Sometimes we'll want to label the glassware. You can write directly on the glass with a Sharpie. It's easy to erase. A lab coat or apron. That's optional here. That's required at other schools like UCLA. UCLA will require 100% cotton lab coat. 100% cotton lab coat is quite expensive, but it's fire resistant. Here, we're not necessarily looking for fire protection. We're just looking for protecting your clothes. And for protecting your clothes, you can go to Amazon and buy like a $15 lab coat. And in fact, that's what I have. I have a $15 lab coat, but that was like 4 years ago, so I'm not sure what the price is now. Probably not changed much. But this is nice to have for lab. This is also required at UCLA. They require the students to wear nitrile gloves. Nitrile has better chemical resistance than latex, and oddly enough, they have better readability. So not only are they more comfortable to wear, but they're better overall for most chemicals. They don't protect you from all chemicals because some chemicals can leak through both latex and nitrile, so you have to be careful. But nitrile gloves, you can buy those at the supermarket.
We don't sell them here. Lab coats we do sell. I think they're offered at the bookstore. And the bookstore has 100% cotton if you want to get that. Those are comfortable. All right, everything's required.
Attendance, especially attendance at lab meetings. We'll talk about that. You have to take all the scheduled exams, quizzes, homework.
Complete the labs and the lab reports. So we're going to have 4 midterm exams. Each midterm exam is worth 100 points. And we'll spread those out evenly. So we have 16 weeks. So we'll have a midterm exam about every 4 weeks. And then we have a lab almost every week. We're going to have 10 labs with reports. So you can, and the reports are going to be worth 12 points each. So that's 120 points per lab. Now, at a school like UCLA, the lab course and the lecture course are separate, but here the lab course and lecture course are combined. So it's only 120 points out of the 100 points. So you might think, okay, I don't want to deal with the lab because it's a lot of work and it's only worth 120 points. So if you subtract that out of here, then you can still get 680 points, and 680 points is enough to pass the class. So you might think, oh, I'm going to just make this skip lab every week. It'll save a lot of time. But you can't do that because we have articulation agreements. And articulation agreements is these agreements with like UCLA or other schools. They say, well, since your lab and lecture are combined into one course, we can't have a student fail lab and get credit for transfer, with the lab and the lecture. And so what we have to do here is this. It's worth 120 points, and you have to have at least a passing grade. That is, the passing grade would be 65% of those 120 points. If you can't get 65% of those 120 points, then you automatically fail the class, regardless of how well you're doing. So you could be getting A's on all the exams. This happened actually once, where I had a student who had Chem before and didn't want to do the labs, but ended up getting A's on all the tests. But they missed so many labs that they had to fail them. So just be aware of that. The labs especially are required. Now, if you do miss a lab, sometimes you can make those up. It depends. Other times you can't make it up, and so you just have to eat those points, but try not to miss the lab. As well as the exam days. Homework, there's going to be 18 chapters worth of homework, 5 points each, so 90 points of homework. We'll have some quizzes. The quiz point total, I'm thinking of increasing this to make it closer to an exam score. So this might go from 30 to 90 points. And that will adjust this, but the exam points will be the same. The final exam points will be the same. The final exam will be 160. All the points are equivalent, and so a quiz, 1 point on a quiz is the same as 1 point on the final. And so the way the grades are going to be distributed will be 90% and above will be an A, and the cutoff for B is 80. The cutoff for C is a little bit wider, it will be 65 for C. And so you need this both for the lab and for the entire course to pass class. Okay. All right, if you need any special accommodations for the exam or the labs will be a little bit difficult, but you can work with the Special Resources Center and see if they can accommodate you with us. So let them know, and then they'll contact me.
The quizzes are going to be a bit more difficult because the
Quizzes are just going to happen on lecture days. I don't have those written in the syllabus. Yeah. But I can work with you for accommodations for quizzes if you need. Okay, if there are any changes, I'll announce that in class. Sometimes I'll post it on campus, but most of the time I'll just do an in-class announcement. Okay, a note on cheating. Academic honesty is mandatory. Getting help. There's free tutoring offered by the library, but they don't start this until later in the semester. I think like the second or third week. The tutors on. You can check, maybe they have a tutor right now. There's Mesa. There's going to be a Mesa tutor and Mesa facilitator. This is a free program. If you haven't heard of this, there's no long-term commitment, but there is a commitment. You have to sign up for it and then attend. There's a website, Ally. I'm not using it, but you can access it. I think the practice quiz is there. And then there's other website feeds. And then what I do, like I say, I use our textbook primarily, but I'll look at other textbooks as well. And so this is something I used to do as a student all the time. And we have a library of old textbooks in Chem 106. And so you can look at those textbooks. If there's particular topics that you're having a difficult time getting those to click, you can check those. And number 5 would be office hours too. We talked about that. So let's take a look at the schedule next. Were there any questions on this? All right, so we're usually Monday, Tuesdays, Wednesdays. Monday and Wednesdays are lecture days of 3 hours each, and then on Tuesdays we have our lab days. Labs are primarily just going to be like a discussion of the laboratory experiment, followed by the experiment itself. Sometimes I'll throw in some lecture material here. So tomorrow I'm going to talk about chapter 2, and we'll do the lab. The reason is the lab's very short. It won't take us very much time to get through that. Next week, this week, we don't need the safety goggles. Laboratory burner, we could do that safely without goggles. Experiment 2, we don't need goggles for this. However, experiment 3, we should have goggles for Charles though. And so I'll talk about that as we get closer. So you have some time to get to all of them. So today we're doing the class overview, chapters 1 and 2. We'll probably just get through chapter 1 here and we'll start 2 tomorrow. But we have 19 chapters we have to cover. And so we're just going through these in numerical order, 1, 2, 3, etc., all the way to 19, which we'll cover the last week. Chapter 19, oxidation production reactions, redox reactions. So 19 chapters in 16 weeks. That means we're going to go more than 1 chapter a week. So some of the chapters are a little longer, some shorter. And so the amount of time per chapter is going to vary. We're going to have 4 exams that are spread out evenly. Our last exam, midterm, will be here. The exams are on lab days. And so we'll be doing the exams in the lab. The lab is not here. The lab is in room Chem 164. Our lecture room is Chem 105. Our first exam is going to be, midterm exam is going to be in the 4 weeks here on March 5th, exam 1. Now, what material is going to be covered on exam 1? Well, if I look at the chapters, I'm going through chapters 1, 2, 3, 4, and 5. It looks like I'll finish chapter 5 right before exam 1. But what most likely is going to happen is exam 1 probably is going to consist of chapters 1 through 4. Probably I'll throw 5 in the following exam. That way you have time to work on the homework. Yeah. Well, the homework assignments can be quite long and time consuming. So it looks like exam 1 will have chapters 1 through 4, and the homework for chapters 1 through 4 will be due. Now the homework due date will be on exam day. So if exam 1 covers 1 through 4, then all the homework for exam
one will be due on this day before class. The homework, you'll scan your work and then upload it onto Canvas. They'll have a link. And you scan it into a PDF file, and not as a JPEG or a photo. Well, make sure you scan it as PDF. And so you need an app like Genius Scan or one of those to do that. And it will be a little bit of work to scan all these pages. Okay, so what is the homework? The homework you'll need the book for. And I'm going to have another PDF here for, this is the 6th edition. Because this homework is based on the 6th edition. I just bought the 7th edition today, so I'm going to cross-reference it. For the most part, the homework problems are the same. They just added one additional section, so it just shifted the sequence off a little bit. But I'll get those. So what's the homework? There's no chapter 1 homework. Chapter 1's pretty short. There should be a chapter 1 homework, but they didn't make any here. So we're going to start off with chapter 2. Chapter 2, there's 29 problems. That takes some time to do. So you have to make sure you have enough time to be able to read the book and do the homework and prepare for the exams. Chapter 3 is quite a bit longer, 44 questions. So this is going to be quite an involved homework assignment here. And then chapter 4 is fairly short at 12 questions. But what's not given is how long each homework problem takes. Like, so, for example, if there are 12 questions here and you're working on, let's say, number 37, and you've been working on it for 1 hour, what should you do? Should you start to worry? Let's say I'm working on problem number 37 for 1 hour, I would start to worry. Because, I mean, if this problem took 1 hour, well, all the problems take 1 hour, it's going to be 12 hours worth of homework right there. And then this would be like 44 hours. So what you want to do is there's a balance, and the balance is between working at the problem and persevering through the problem versus giving up. But it's not really giving up, because what I'm talking about giving up is consulting the solutions manual. Now, another advantage of the book is it has a built-in solutions manual. Usually you take a class and there's a student solutions manual where it has the worked out problems for selected numbers. These are mostly blue numbered problems. And so the solutions manual is inside the book. So let's say number 37 is stumping you. Well, don't let it stump you for too long. You probably should just consult the solutions manual and just see how it's done. And the worst case scenario is just copy it from the solutions manual. And so in theory, even if you weren't able to do all the problems, I assume you can copy it from the solutions manual and write it into your homework notebook or into your homework assignment, and then scan that. And so in theory, you should be able to get 100% on the homework. In practice, only about 10% of the class gets 100%. For some reason or other, maybe people just run out of time for homework. All right, so that's something I also did as a student. So as a student, I never read the chapter before. It took too much time. I always read the book after. And the other thing was, for the homework, if I got stuck on a particular problem, I just looked at the solutions guide. Now, the good thing about UCLA is, when I was a student there, was they had the complete solutions manual. That is, they had the instructor's solutions manual, which had the answers to all the problems, versus the student solutions manual, which had the answers to a select number of problems. Here, you just have the student solutions manual, which is, again, incorporated in the textbook. So that's another reason why the textbook is kind of nice to have. You don't have to buy a separate solutions guide. All right, so when is this homework due? Chapters 2, 3, and 4. That's going to be due on exam one day. And then 5, 6, etc. will be due on the next exam. So we'll take a break pretty soon. Yeah. Continue here. The experiments, you see experiment 1, 2, 3. This looks like it's going to be in numerical order, but it's not. Because if I go, this should be experiment 4, but instead we're going to do a handout. It's going to be exercise A, which is nomenclature. And then we're skipping 4 entirely and doing 5, 6, and 7. Actually, this is a typo here. This should be 5, 6, 7, and 12. So most of the experiments are one-day experiments, like this. One day and we're done. However, 5, 6, and 12, that's 4 experiments. And we're going to do those 4 experiments over 3 days. Well, 4 experiments in 3 days, that's kind of tight. And so what I've done to these is I'm going to omit sections, parts of the experiment, so we can accomplish it in 3 days. And so it won't be as long. What happened to 11? We're skipping 11 and going back to 10. And so 10 is one experiment, but we're going to do that over 2 days here, titration. So we're going to break this up into 2 parts, part 1 and part 2. Then we're starting experiment 8 here, which we're going to finish. This is a paper lab, so you can finish it at home as well. And then we're going back to 11. Experiment 11 we're going to do over 2 days here, part 1 and part 2. Part 1 I call the known, part 2 I call the unknown. Then exam 4, and here we're just going to lecture on that lab. That should be 12 labs there. All right, the final exam here is going to be comprehensive. That is, this final exam is going to cover all the material from chapter 1 on through chapter 19. So here, I can't, I have to cover chapter 19. And so I'm going to introduce redox earlier. So it'll make this a little easier at the end, so we don't have to cram it all in right at the very end for the semester. All right, any questions on the schedule? All right, let's take a break for 15 minutes, and we'll start out at, let's say, 2:40. To the 6th edition PowerPoint. And so that's what I have here, the 6th edition. The only difference is maybe sometimes the section number will change, but the name won't change. So you just look at the name and see what the topic of that particular section is. And then we're going to do chapters 1 and 2. So we'll start this here. You can download these by clicking this link. And that's what I did. I already downloaded this. But I'm going to go ahead and download it again because I've annotated this one from the morning. So what I'm going to do is I'm going to post the annotated one here. Like, for example, this is what I talked about this morning. So I'll save this. I'll probably just put in the section number here. This was from section 1216. And then the date, which is 02/12/24 here. And then I'm going to post this on Canvas. So this is how I'm going to do my lecture notes here. If you can read that, I have to blow it up. But what I'll do here is I'll go ahead and open this fresh file here. Now, I'm not going to do PowerPoint slideshow because in a slideshow, I can't write on the slide. So I'm just going to do it like this. I'll just try to blow it up as we need it. And let's see how this works if people prefer this.
or I just prefer the more traditional style lecture. As a student, I hated PowerPoint, so I never liked them. But I've talked to others that really like them, so we'll go with this right now. But chapter 1 deals with introduction to chemistry and introduction to active learning. And so Krakalici, the author, has his way of doing active learning, and then I have my way. So it's a little bit different. Let's look at the chapter outline. 1.1, Introduction to Chemistry, Lavoisier, and the beginning of experimental chemistry. So we'll talk about Lavoisier. 1.2, Introduction to Chemistry, Science and the Scientific Method. 1.3, The Science of Chemistry Today. And then after 1.3, Krakalici goes into active learning. And so introduction to active learning, learning how to learn chemistry. So everybody has their advice. I have my advice. I told you, what I do. I like to not spend too much time on one particular problem. And there's another reason for that. One, because there's a balance. There are some instructors that say never crack open the solutions guide, the solutions manual, because you're just hurting yourself. You're not really going to get it unless you put in the effort. And so it's going to require a lot of sweat, they say. And so I think that's fine, but if, let's say you have a job, your job is to go and study a forest. Are you going to spend all your time just looking at one tree in the entire forest and then run out of time for everything else? No, that wouldn't be very effective. And so the other reason I don't spend too much time on one particular problem is because, the homework assignment I just showed, that's the minimum homework required. But there is no maximum. And so let me tell you a story of when I was a student at UCLA. When I was a student at UCLA, there was a person sitting next to me, and that person got the high score on a test. And this was my first quarter at UCLA. And that particular test, I did pretty poorly. I got like a D on the test. And this is a chemistry class, so it's not like I should be getting D's on a chemistry class as a chemistry major, but it happened. And so I figured I had to change something. So then I started looking into how people study and what advice people have for studying. So I thought I better change the way I study because I spent so much time preparing for that test. And I couldn't understand how I did so poorly on the test. So I asked the student next to me how they studied, how they prepared. And you know what he told me? He said he did every single problem at the end of the chapter. Not just the ones that the teacher had assigned, but all of them. And I thought, that's impossible. You can't do that because some of those problems took me 1 hour to do. And so how can you have that many hours to do it? And it turns out he didn't really do it. What he did was he looked at the question and then looked at the answer. At UCLA, like I said, they had this teacher solutions manual, not the student's solutions manual. So you could do that. You could look at, but even here, you could look at all the blue problems and then look at the answer. And so what were they doing? Well, they were quickly going through because, if you were just studying one tree and somebody asked you a question, okay, what's the biggest tree in the forest? Would you know, having looked at just one tree? What's the smallest tree in the forest? What are the shapes of the trees? All these types of things. Well, if you spend all your time on a limited set of homework problems, you're not going to see the whole spectrum. And the whole spectrum in chemistry is, what are all the methods, what are all the tools that people use to solve these homework problems? Is there a limited set or is there a finite set? When you look at it, is there something that repeats? Oh, they're always doing this, or oh, they're always doing that. These things you don't see if you're just looking at one. And so after I heard that, I started doing the same thing, and it made a big difference. It made a big difference because I saw every single possible problem in the book and how they solved it. And then I cataloged those in my head because I thought, oh, this is just a repeat of that, but they twisted that. Or this is just like this one, but they did this. And so you go through and you see that. And that's very important because at UCLA, oftentimes they'll give questions that are not in the book that were not in lecture. And students will go, that's unfair. You know, if it wasn't in the book and it wasn't in the lecture, then how can they test us on that? You know, never heard it before. But they don't care, because at UCLA, what they want is they want to get a distribution. They don't want a bunch of people stacked up at 100%. If you have like 3 people getting 100%, then how do you spread those people out? And so they make the test so that nobody can get 100%. And so there's always going to be that one challenge problem, that one hard problem that people aren't going to get, you know. And if somebody gets it, it's just one person, and then they know that they're like a standout, like a star student. And so, how do you get prepared for questions that aren't like the lecture, that aren't like the homework? Well, how you prepare for those is you have all the ones that are in the homework mastered. You have all the ones in the lecture mastered. And that way, if there's additional twists on the problem, then that's usually what happens here is you'll see a lot of repetition. You know, pretty soon, now this problem looks very similar to that problem. You use the same method. And then you see all these twists. There's a finite number. There's not like an infinite number of things you can tweak on a problem to do it. And so, I recommend that, but you could read through his recommendations here, learning how to learn chemistry, 1.4, 1.5, Introduction to Active Learning, your textbook, and 1.6, a choice, you know. How many hours are you going to devote to this? You have to devote quite a lot of hours. So we're just going to focus on the chemistry stuff, you know. And then you could use those tips from Berkeley too if you want, or use your own or use mine, whichever works for you. All right, so let's go through Introduction to Chemistry. So let's see how Carpellicci defines chemistry. Carpellicci defines chemistry as science that studies how molecules behave. Would you say that's the definition of chemistry, the study of the science, or no, the science that studies how molecules behave? Is that a pretty good definition? Or would you want to change it a little bit? What would you want to change with that definition? And in other words, do chemists only study molecules? And now molecules is a particular structure, like water. You know, did I tell you about water already? Sometimes I have these deja vu moments because this is a repeat of this morning, so I can't remember. Yeah, it's a pure substance, and now with water, you can take smaller and smaller drops. What's the smallest drop of water you can get from water? The smallest drop of water you can get is a drop of water that consists of one molecule of water. Now, one molecule of water can't be broken down into anything smaller. So the smallest piece of water, the smallest particle of water is called a molecule. And if you take that molecule and try to make it smaller, it's no longer water. Right? What we have in water, do you know what the composition of water is? H2O. And that means we have 2 particles of hydrogen. Those particles of hydrogen are called atoms of hydrogen. So we have 2 atoms of hydrogen, and they're going to be attached to an atom of oxygen. So that's what gives it the composition H2O. 2 atoms of hydrogen, 1 atom of oxygen. Now, you kind of break that apart, but it's no longer water. So in the sun, there are no molecules that exist in the sun, you know? The sun is such high temperature. Now, temperature is related to kinetic energy. Kinetic energy, you know, we talked about energy, light energy, this energy, that energy. Well, what kinetic energy is the energy of motion. And the sun, there's such high kinetic energy that things are moving fast. And when they move fast, they can collide with high energy, tremendous energy, enough energy to break the molecule apart. But when the molecule is broken apart, we're left with fragments of the molecule, which are with hydrogen atoms and oxygen atoms. Those don't behave like water. But chemists are interested in atoms as well as molecules, as well as other things. There's certain things that kind of annoy chemists. One of the things that annoy chemists are people talking about molecules of gold. Have you ever heard of a molecule of gold? You know, Not really. When people are talking molecules of gold, then you think they don't really understand chemistry or the definitions of chemistry, because gold doesn't occur as molecules. You know what gold occurs as? It's an element, but the smallest piece of gold is not a molecule. Well, the smallest piece of gold is an atom. So we could talk about atoms of gold, and these atoms of gold can cluster into crystals. So we can get crystals of gold, which are, big conglomerates of gold atoms. Other things that bother chemists would be people talking about molecules of salt. So if you have like table salt, what's the smallest piece of table salt you can have? Is it a molecule? Do we call it a molecule? We don't. Although table salt, do you know what table salt's made out of?
Sodium chloride.
Sodium chloride. It's made of sodium and chlorine. Sodium chloride. And there are no molecules of sodium chloride. It occurs as lattice. So one of the first things we'd get rid of is maybe cross it out and call it the science that studies how matter behaves. Don't you think that would be a little better for the definition? We'll talk about matter, because then it won't be so restrictive, because not everything occurs. That means, like, for example, somebody might say, oh, that means you don't study gold. Of course we study gold. And gold doesn't occur as molecules, in the normal sense. Oh, you can make a molecule of gold, but a molecule of gold is not discrete. So a molecule of water is discrete. A molecule of water has to have how many hydrogens? 2. How many oxygens? 1. What if you said, okay, I'm going to make a molecule of water that consists of 3 hydrogens and 1 oxygen and call it H3O? Would that be considered water? No. What if you said, okay, I'm going to make a gold with 3 gold atoms? Then yes, it's okay, because gold does not occur as discrete. You could have 3 gold atoms bonded together. Maybe that's a little fragment, a little tiny crystal of gold, right? And nobody can dispute that. And so if gold molecules always occurred as 3 atom units, then we'd say gold is molecular. But you can have a little piece of gold, you can have a big piece of gold. It just depends on how big you want it. Could you have a little piece of water and a big piece of water molecule? No, but yes, as a bunch of water molecules, yes. And so we probably should change this to matter, and then that's okay. But then we go into what is science? What do scientists do? If you want to come up with a quick definition of what scientists do, you can think of one of the most influential, famous scientists out there. Who would that be? Somebody just told me that. Somebody told me the 3 most influential historical figures. Do you know the 3 most influential historical figures? Somebody told me that Newton was ranked at number 2. Newton. And so Isaac Newton did physics and math, and have you heard of Newton's equations and gravity and that stuff? So in other words, what did Newton do? Well, he observed what? You might have heard this story. He observed what falling from a tree? An apple falling from a tree. So Newton observed an apple falling from a tree. So that's what scientists do. You know what scientists do? They observe nature. Like if you're a scientist going out to study the forest, what do? You observe the trees in the forest, the plants, the animals, whatever else, right? You're just observing nature. Do you do anything else? Do you or just observe?
Collect data.
I guess you could collect data, but the data is still just observation. So that's what scientists do. Scientists observe nature. And so that's what chemists do. Chemists, well, if you're a botanist, then you're observing the plants. If you're a biologist, then light. But chemists, they observe matter, so they're observing both like living things and inanimate things as well. So we're just observing. Well, here we go into molecules. Molecules are the smallest unit particle of pure substance that can exist independently and possess the identity of substance. And so this makes it seem like chemistry doesn't study mixtures, because is a mixture a pure substance? No. Mixture isn't, because the composition mixture can change depending on what it is. There are other things that are pure substances. Did I talk about hydrogen peroxide?
You know what the formula for hydrogen peroxide is? Hydrogen peroxide's formula is H2O2. And so rather than having one oxygen, it has two oxygens. And it also forms a molecule like water, but its properties are quite different. You know, there's its properties are significantly different. So, for example, you could drink water, but would you want to drink hydrogen peroxide? Definitely not. And so there's a joke. You might have heard this joke before, but two people walk into a bar. You know, they're friends. The first person says, "I'll have an H2O," you know, and the person's friend says, "I'll have an H2O2." And so the first person's fine, you know, gets hydrated. The second person ends up dying due to hydrogen peroxide poisoning. So that's the joke. But anyway, we have that. So this is a little bit too narrow. Chemists ponder on things that make up the universe. Are there any molecules in the sun? No, there are no molecules. Why? Because of the kinetic energy. You know, there's too much energy. What it does is it pretty much destroys the molecules, breaks them apart into smaller pieces. So there are atoms in the sun, and there are other things in the sun as well. And so molecules don't make a whole lot. So I would change this a little bit, but we already talked about it. So I'm going to move on from this slide. And so chemistry, what do chemists do? They observe nature. When we observe things, we can be quantitative or qualitative. So what's the difference between quantitative and qualitative? So for example, when Newton looked at the apple falling from the tree, Newton might have said, wow, that was fast, you know? Or did Newton take measurements? How long did it take, you know? Rather than saying it was fast, he might have said it took this many seconds. Well, that's the difference. Qualitative would be it fell fast. You know? It didn't take very long. How fast was it going when it hit the ground? It was going very fast versus it was going this fast. And so we want to take very detailed, what we call observations. And these detailed observations, when we do this, we design an experiment so that we can take detailed observations. So scientists like to do a lot of experiments. That is, when they observe nature, they like to be as quantitative as possible. And so they'll design experiments to be as quantitative as possible. And so this brings Lavoisier. Lavoisier is thought of as the father of modern chemistry and wrote this treatise on chemistry here. It's French. It's published in 1789. You don't need to know these details here. Conducted experiments and formulated theories. Revolutionized thinking that was accepted from the time of the Greeks. So what preceded Lavoisier? I mean, why was this so revolutionary? And so really the importance here is this. Lavoisier was at the transition. Prior to Lavoisier, chemists, you could call the chemists alchemists. And so what's the difference between chemists and alchemists? Do you know? So here, predating, so this is what is talking about revolutionizing thinking, because prior to Lavoisier, chemistry was alchemy. And the difference between alchemy and chemistry is that alchemy has another component to it. Alchemy is part science. Science is observation of nature. So alchemy is part science. That is, we have the observation of nature, and that's all. But alchemy also included like magic. And magic isn't necessarily science. And so prior to Lavoisier, it was a mix. You know, the scientists of the time were alchemists, and this alchemist included magic in addition to science. Now, what type of magic are we talking about? The type of magic we're talking about is, let's see if I have my alchemy thing still set up here.
Well, it looks like scientists to me, like medieval scientists. This looks like a medieval periodic table. Periodic table listing what the universe is made out of. But there's some additional stuff in this periodic table. I mean, we have stuff like the, air. Um, this is kind of mixed up because air is considered a mixture. Air. A pure substance has to have a fixed composition. So water is always H2O, but sugar water isn't always like 50% sugar, 50% water. You would have different things. Air is considered mixture. It's a mixture of nitrogen, oxygen, and other gases. Whereas some of these other things are pure, like gold. Gold's pure, sulfur's pure, being a substance, not a mixture. Silver's pure, potassium's pure. Salt depends sodium chloride, yes, pure, but you can have mixtures of salt with water, pure. And so air is kind of out of there. It doesn't quite belong there because it's not fixed like the others. But of course, alchemists will study air. It doesn't matter. Chemists will study air too, and they're very interested in that mixture. But fire is interesting. Fire has high kinetic energy, like the sun. The sun's a giant fireball, and that giant fireball is lots of energy. And we see that light. Light is energy, right? We see that light coming out. The same thing with a flame here. You see the light coming out. That's matter too. People are interested in matter. That's what they call the fourth state of matter. Have you ever heard of the fourth state of matter? Fourth state of matter is what they call plasma. The sun's a plasma. The flame is a plasma. So we're interested in plasma as well. What are the other three states of matter? 1, 2, and 3. Yeah, solid, liquid, and gas. And plasma. But what's this thing in the middle? The philosopher's stone. Is that from observation? You can observe air. You can observe all this other stuff. But do you know what the philosopher's stone is? No, it's not that. It would be great if it existed, But the philosopher's stone is this object or stone or whatever it is that converts base metals into gold. Wouldn't that be fantastic? I want some gold. I'll just use the philosopher's stone, convert it into gold. That would be great. That would be great. But would you call that science or would you call that like magic? Maybe magic. I don't know. Because science is based on observation. And this is what Lavoisier did, He made science based on what scientists do is they just observe nature. And they look for how nature behaves and the patterns of nature. And then that's all. They're describing nature. Scientists describe nature. And so what part of nature are they describing with the philosopher's stone? Did somebody find it? Well, maybe somebody found the philosopher's stone, but they're keeping it secret. We don't know. But if somebody found it, then that would be science, because that would just be an observation. So that's the magic component. What about this liquid here? Do you know what that liquid is supposed to represent, I think? That's supposed to be the elixir of life. Have you heard of the elixir of life? The elixir of life, if you drink it, you know what will happen? You'd live forever, You'd live forever. Do you think that's based on observation? They found the elixir of life in some remote part of the forest. This is why you want to go out in the forest and study everything. You don't want to focus on one tree. You want to find the elixir of life, right? But do you think that's based on observations? It's looking at nature, taking careful measurements, experimentation, that kind of stuff? No. So that's another magic component of this. And so what Lavoisier did was this. He shifted it and got rid of the magic. If there's an elixir of life, so for example, in other words, there's no scientific police force, where they find bad science and eliminate it. It's self-policed.
Have you make a comparison to some substance that can turn other metals into gold to trying to find other properties like graviton to find like how gravity actually exists at all.
The difference is there's got to be some kind of evidence in support of it. And so if they're looking for, let's say, a graviton or some kind of field like a Higgs field or something like that, there's got to be some kind of evidence in support of that. Now, that evidence can come from observation or it could come from theory. But the theory is usually based on observation. And so you have some very talented, let's say, theoretical physicists looking for certain things. But if what they're looking for doesn't agree with the observations, then who wins? Do the experimental physicists or the theoretical physicists? If the theoretical physicists predict something, but the experimental physicists see something else, then who's right? Well, who always wins will be the observations because those are facts, scientific facts, whereas other things aren't. And so something like this, if you had the elixir of life, and I do have the elixir of life here. I mean, I could sell this to you, for $100 or so. You can have it cheap. I mean, elixir of life. Would you buy it? I mean, you can buy it if you want. No, this is the elixir of life. If I have the elixir of life here, and I'm gonna just I mean $100 just to cover my cost because I gotta go refill it occasionally. Would you buy it? Okay, you're able to. I can sell this to you after class, so you could just come talk to me. Yeah, $100. No. What we want is you'd be skeptical, wouldn't you be skeptical? You'd want to see some evidence to support that this is. You want to see some observation. So you might say, okay, you drink it, and then you'd have to wait a long time, or maybe a short time until I die. But you'd want to see some evidence, some observations to support this, wouldn't you? And so that's one of the difference. You aren't going to believe some. Even though they're dressed like they know it for sure, and that they probably can convince a lot of people that they have the elixir of life, but you'd want to see something to support that. And so the difference is if they're having something called the graviton, then they're going to design experiments to get some evidence to support it. Now, if you have the elixir of life, you want to do the same thing. You want to design experiments so that you can see that you can support it, or you want to see some observations. What observations do they have that lead you to trust them, that they have the elixir of life? And so that's the difference. The difference is we want to see some observational facts that support this. And if there are none, that doesn't mean it doesn't exist. That just means that you're going to wait and see before trusting that. And so Lavoisier was the first. So he's just saying that what do scientists do? Scientists just observe nature, and that's it. It's like Newton. Once Newton did that, he came up with Newton's laws, and then you could use those laws to make predictions of how nature is going to behave. So if an apple falls like that, what happens if a banana falls? You can make predictions based on this. Well, one of the, and we're going to talk, the phlogiston theory. Now, theory we reserve. We have very specific ways that we use these words. And so theory is used frequently, like you have a theory of who murdered that person, or you have a theory of this or a theory of that. Well, normally when we hear those types of things, we think hypothesis, because the theory has to meet a higher standard. And so there are two competing hypotheses at the time of Lavoisier. One hypothesis was phlogiston, and the other hypothesis was something else, which Lavoisier proposed, and I'll talk about that. But what is phlogiston, the hypothesis? The hypothesis of phlogiston is, let's say you burn a candle. When you burn a candle, what happens? The candle kind of disappears. Or you burn wood, what happens? Well, the wood gets converted into ash. And the candle and the ash, they become much lighter. And so they're losing a lot of matter. And so what happened to the matter that was lost? Well, the hypothesis goes like that. When something burns, it releases phlogiston. And that's why you have a lot less. You have a lot less candle, you don't have the wood anymore, you have ash. And so buy into the phlogiston hypothesis. Well, you want to see some supporting evidence. And so what Lavoisier did was he burned some phosphorus and some mercury. And then took careful observations. And so one of the things that happened was this. So not only did he look at the substance that he burned and what was left over, he looked at the air that was involved in it. And tracked the air with a balloon here. And when he burned the phosphorus, it looks like some of the air had disappeared. And so if you are one of the phlogiston proponents, then how would you explain this? Because when you burn something, according to the phlogiston hypothesis, the phlogiston should leave the burnt substance, the burning substance, and the residual should be left. So this experiment was designed basically this to counter the phlogiston hypothesis. In fact, this disproves the phlogiston hypothesis because there was no phlogiston left there. Does that make sense? But Lavoisier took this a step further. Not only did he end up with more, the ash weighed more than the initial, he weighed this before and after. So can you weigh air? Does air weigh anything? Or is it weightless? Like, for example, if you have do you have one of those can dusters or can of air? Can you tell the difference between a full can and an empty can? An empty can is a lot lighter. Right? And so even though it's a bit of a pain, you can weigh air. Like if you're a scuba diver or something like that, you can tell an empty tank versus a full tank. A full tank is going to weigh a lot more. And so what he was able to do is he was able to weigh this before and then after. And you know what he found out? That it weighed exactly the same. And so the total weight before and the total weight after is the same. If the total weight before and after is the same, then did he lose anything? Was phlogiston lost? No, phlogiston was not lost. In fact, you know, how did we define matter again? Matter is anything that, occupies space and has mass. And so, in other words, did we lose any matter here? We didn't lose any matter. And so all the matter that was in here before is here, but this is an example of a chemical change. In a physical change, like freezing water, you know, you'll start off with liquid water and end up with ice, but it's still water. It still consists of H2O. That is, its composition didn't change. What happened here is that the phosphorus, this is no longer phosphorus. You can't burn this stuff. And so what must have happened is it rearranged. So the matter was rearranged in this to make new substances. And so that would be the definition of a chemical change or a chemical reaction in which the substances, matter gets rearranged to make new substances. So this is one experiment. Now, with the experiments, what you do is you just make sure they're reproducible. And so you redo this with different amounts of phosphorus and different conditions and see if you get the same result. And what he did was he got the same result. And then he tried this on different systems. And so the next thing he tried to burn is mercury. And the same thing happened here. When you burn the mercury, the mass before, that is the amount of matter before, is equal to the amount of matter after. Now, chemists use mass and weight interchangeably, but technically they're different. And so the weight before and the weight after were the same, which is true. But do you know the difference between mass and weight? The weight is dependent on gravity. So, for example, if you weigh yourself on Earth and then weigh yourself on the moon, do you know you're going to be like 1/6 the weight on the moon? You'll be a lot lighter. However, does that mean you lost 5/6 of the matter in your body? Maybe part of an arm or a leg? No. The amount of matter is the same. And so mass is the measure of the quantity of matter. And so weight's usually in pounds, mass is usually in like kilograms, something like that. And so the amount of matter is the same. But we use the terms interchangeably. So the mass is the same, the weight is the same, before and after. And these are just observations. This is just factual observations. And these factual observations will refute the phlogiston theory. And this is how science is policed. Science isn't policed because Lavoisier didn't, like, for example, declare himself like the science. He's not the science. Usually what people do is everybody's a scientist. And everybody, might have skepticism. You can support ideas. You just have to be able to defend them with observations, with experimental facts, those types of things. And so what we don't want in science is Lavoisier or the proponents of phlogiston, they don't want to censor the other side. What they want is they want them to discuss this and reach some kind of mutual consensus. Now that once that mutual consensus is reached, then we go from a hypothesis to a theory. And so the difference between a hypothesis and a theory is the theory will have widespread acceptance. The hypothesis won't. The hypothesis is still up for debate. Uh-huh.
So what is the phlogiston? Like, you can say that if you burn wood, like, phlogiston escapes, like what?
Yeah, if you burn wood, phlogiston escapes, and what escapes is this balloon would grow bigger. And what it escapes is the matter just gets rearranged in the wood, and so it gets rearranged with CO2 and water, and so we have CO2.
What was the proposal with this? If it says that it leaves, but if you're trapping it, then it can't leave. Kind of like is what the theory is.
Phlogiston, the hypothesis of phlogiston is that phlogiston was something that was contained in all things that could be combusted and all things that could be burned, and it's something that leaves when you burn it. But the thing is, nothing left. When if we're looking at matter, no matter left, and what is the universe made out of? Is made out of matter, and so nothing left, and nothing came in because all the matter, phlogiston didn't come in necessarily because I guess the phlogiston proponents could say there was phlogiston in the air that went into the ash, or something. They might have come up with some ad hoc addition to it. But basically, phlogiston is like the elixir of life. Somebody proposed it, but what evidence do they have to support that proposal? And the evidence that they had to support the proposal was that the mass declined. All of a sudden the candle was a lot smaller. All of a sudden the tree was converted into ash. And that was the evidence, but are there alternate hypotheses that can explain those same observations? And then what we do, what scientists do is they'll look at that, and then they'll see what evidence supports a particular hypothesis. Uh-huh.
I think another example you could think about is like how people thought that when the soul left the body, it would be like get heavier, or like it'd be like it was like heavier. Yeah,
stuff like for
As
sure. And so the thing is, before you buy my elixir of life, or before you do you want to devote your life to finding the elixir of life? Maybe you have a fortune. Let's say you inherited a fortune, and you're going to devote that fortune and the rest of your life to finding the elixir of life. Will you?
And well, that's what the alchemists did, but what observations led them to believe that there was an elixir of life out there? Well, something that comes close, and now let's bring this up to more modern times, is, have you ever heard of this author, David Sinclair? He is a professor at Harvard. He has a lot of talks. He talks about aging backwards. Have you heard of that? We're getting younger. You think that's ridiculous, isn't it? That's like the elixir of life, or slowing down aging, or living like forever. He proposes living forever. Is he out? Is he like is alchemy making a comeback or what? That's what some people thought. Some people thought this guy ridiculous. But there's a big difference between him and the alchemist. And he wrote a book. I'm about maybe 3/4 of the way through the book. Have you heard of his book?
I've never heard of his book, but I've heard about this theory.
Yeah, his book, I think it's, I'm in the middle of reading it, but I got distracted, so I haven't read it. His book is called, let me see what his book's called. I'd recommend it. It's a good book. Oh, here it is. Lifespan. Yeah, I have this book. Although this is an older edition. I mean, it hasn't been updated. There's more recent data that he has. And so what's the difference between this? Why we age and why we don't have to. What's the difference between this person and the alchemist of the past? They're totally, it's similar in the way that they're looking for immortality, but totally different. You look at the alchemist, there's no way I'm going to devote my life looking for the elixir of life in some remote forest, jungle, or wherever, or trying to make it in the laboratory. But, this person's convinced me to buy some stuff off Amazon. I thought, okay, M&M, I'm going to buy that. Have you ever heard of M&M? You can't buy it anymore because for some reason they stopped selling it suddenly. Yeah, it's a supplement, but it's a supplement that's been around for a long time. There's some weird stuff that goes on. Yeah, for cellular health, exactly. And M&M, and there's other things, metformin, a bunch of other stuff. But the big difference is you read this and you read these experiments and you go, wow, based on those observations, I can believe that. There's a huge difference because for the alchemist, there was no evidence in support of it. For this, there is evidence in support of it. And you can debate him. He's a tenured professor at Harvard. You can debate him and say you're ridiculous, but if you're going to debate, you got to debate the evidence. If he has this observation, and his observations are some of them are more anecdotal, less quantitative. So, for example, I think one of his students' mom started taking it, and then she was like post-menopausal, and then she became pre, something like that. It was really weird. And then they had eyes reverse aging on eyes that they did, and other things. These are actual experiments with observations. So what's the hypothesis behind those? How do you explain those? And so he has some interesting ideas about aging. Aging is being loss of information, DNA, chromatins, and et cetera. So this is a very interesting book, and it's worth reading too. The alchemists are interesting as well. If you're into the medieval alchemy, that's interesting. But this is quite relevant to today, and there's some stuff, and so a lot of people are following his protocol to slow down aging. And the way he's saying is, if you can, let's say if you can reverse aging, let's say if you can reverse aging like 1 year, so you're 1 year younger than your biological age. And a lot of people do that. They say, age is just a number, but your biological age, you can actually be younger. And so there's certain people that take up lifestyles and health, healthy diets to reverse that. And so let's say you reverse your biological age by 1 year, and you do that every year. So next year you reverse it by 1 year, next year you reverse it, and then pretty soon you could start aging backwards. So this is why he's talking about aging backwards and then potential for living forever, possibly, or at least extending your lifespan. Okay, so this is based on the scientific method. The alchemists weren't based on the scientific method. So let's talk about the scientific method next in Lavoisier. So Lavoisier is thought of as the start, of the transition to modern science. And modern science is based on the scientific method. This is not the slide. And this is the other thing. Sometimes I don't use the book, and so it gets tricky because here I don't like this. And so what I'm going to do is I'm going to change it a little bit. And so if I were to test you on the scientific method, I prefer you organize it like this. And so if we look at the scientific method, one thing's the same. Science and scientists just observe nature. And so we start off with observation. We don't start off with a theory. Do you want to start off with the theory of aging, like David Sinclair's theory of aging? Can you start off with that? Did David Sinclair start off with theory? No, David Sinclair didn't start off with the theory of the elixir of life. He just looked at observations, then he started noticing some observations were leading to this age reversal, or at least slowing down the aging process. So we start off with observation, and one of the observations is like burning phosphorus and burning mercury. It turns out we end up with the same mass before and after. And so what we call that a pattern or a trend. So here we had these observations of burning things, and the pattern or trend was the mass, total mass did not change. Didn't change. It's supposed to be didn't. Total mass didn't change. Now you want something that's reproducible and occurs over and over. And if it occurs over and over with precision, then we call it a law. So if we do this, we do it with phosphorus, we do it with mercury, we do it with wood, and we always see the same pattern, then we can define that pattern using a mathematical equation. And that law, in this case, will be just an empirical equation, or we call it an empirical law too. But the equation is just going to be the mass at the end was the same as the mass at the beginning. So mass final is equal to the mass initial. In other words, delta mass final minus mass initial is equal to 0. And that would be our law. Now, where did this law come from? This law came from observation, and empirical just means that. Empirical means based on observation. And we give a name to this. This is the law of conservation of mass. And we know that what is matter? Matter is just anything that occupies space and has mass. So we can convert this to the law of conservation of matter. So when we have a chemical chain, what happens is the matter just gets rearranged. All the matter is still there. And so the law of conservation of matter, which comes from the law of conservation of mass, which, in other words, matter is neither created nor destroyed. This is in below. Later on in chapter 2, we'll modify that. Okay, then we start to think, okay, what's being rearranged? If the matter is being rearranged, how is it being rearranged? And it turns out that matter consists of molecules, and molecules consist of atoms, and sodium chloride and gold consist of atoms, so the atoms must be rearranging. So for example, we might have an H2O that goes to an H2O2. Well, those are two totally different pieces of matter, but the atoms were rearranged in that. Additional oxygen must have come from somewhere. And so we come up with a hypothesis. Now, a hypothesis is meant to be debated. You can come up with any hypothesis, however ridiculous it is. For example, David Sinclair comes up with this hypothesis of eternal life, right? And you might think that's completely ridiculous, but it's fine. Everybody should be. If it is completely ridiculous, then debate him and then squash it that way. But what's been happening in science recently is a lot of censorship. Censorship is very bad for science. So, for example, if David Sinclair, somebody thought his ideas were totally ridiculous and decided to censor him. This is why MNN's not available on Amazon, I think, is because of David Sinclair. And some scientists at Amazon's thinking, well, we shouldn't sell this because he's some kind of elixir of life salesman, And some people believe him to be an elixir of life salesperson. But if you believe that, then debate him and then, come up with alternate hypothesis of why that observation. This is like the whole idea between the origin of coronavirus. Did it come from the lab or did it come from bats, which went on to pangolins and which came to humans,
Which is interesting because if you look at Lysol, it says that it's kind of approved for
Oh.
and barbicides too, for like hairdressers and stuff.
Well, yeah, but this is COVID too, but there's COVID-1 also.
Yeah.
And then actually, speaking of that, there's some other weird stuff that's happening. There's another supplement that I was taking. This supplement is good for, as an antioxidant, is good for flu, whatever else. Yeah. Wow, you know that too. I was taking that. So the last batch I bought was off Amazon, and then all of a sudden it's gone. And the only reason I could figure it's gone is it's got to be COVID related, and it was COVID related because, yeah, it was NAC, but I think they're selling it again. NAC. The reason I started taking NAC was because of this guy, not David Sinclair, but another person, which I'll let me just tell you about briefly here. This other person has this. This other person is a professor of medicine at UC Riverside, and Dr. Schwelt. He has dual appointment. He's a professor of medicine at Riverside and at Loma Linda in Inland Empire. And he had some videos about NAC. So that's why I started taking NAC, and then they stopped selling it because it's anything related to COVID is being censored or banned or whatever. And so,
You take creatine?
No. There are others. I mean, there's just too many. If you take the full protocol for Sinclair, there's a lot, metformin, NMN, et cetera. But if you're interested in this, he has some free. All his COVID presentations are free. And he has a hypothesis about COVID too, about blood clots and that kind of stuff. Although that hypothesis might be disputed. It's probably a different mechanism now. But it's fine. Everybody can propose a hypothesis. You just have to have observations to support it. Just like alchemists. Nobody should censor any alchemist. Alchemists can propose elixir of life. You just want some evidence and some data to support it before buying it and consuming it. And so that's what I mean, you can make your own judgment. I'm not a medical person, and I'm not proposing any treatment, but you want to look at what the observations and data are, and so you can make up your own mind. I don't want to be told, unless, of course, there's plentiful evidence to support it. But that's how science works. Science is full of skeptics, and these skeptics, you go to a scientific conference, that's all it is you have people hypothesizing this, hypothesizing that, and then, each side is trying to convince the other side to adopt it, and then you'll get a theory. That's what we'll have. So anyway, yeah, he has a video on NAC as well, and so I was taking NAC. I stopped taking it. I don't take it, and I'm only 2/3 of the way through this. So whether you take it or wait for some randomized controlled trials, up to you. And that's the way it should be. But let's go back to this. So hypothesis is a fundamental description. So what's happening to the matter? How's the matter being rearranged? And so that's what we want to know. And the hypothesis here are that matter consists of atoms. Even molecules can be broken down into atoms. You put a molecule of water in the sun, it's going to be broken up into atoms, hydrogen atoms and oxygen atoms, and it's going to be rearranged. And so matter is made up of the atoms, and these atoms get rearranged. So the hypothesis here are the atoms are rearranged. But we have to have atoms. This requires atoms because can you find a water molecule in there that has, let's say, 2.1 hydrogens for every 1 oxygen? No. In other words, if you can take hydrogen and get smaller and smaller pieces in any fraction you want, then there's no limit. You could take 2.1, you could take 2.09, you could take 2.11 parts of hydrogen and mix it with oxygen. But the atom is the smallest piece of hydrogen that exists. And so the smallest amount of hydrogen we can get is 1 hydrogen atom. And those are going to combine with 1 oxygen, 2 of these hydrogens, 1 oxygen to make it. And so the hypothesis is atoms. And this eventually led to the theory, and that we call atomic theory, that matter is made up of atoms. And this is atomic theory. Lavoisier didn't do this. Lavoisier got up to about here. Spelling's probably wrong. But the theory part, there were inklings of theory before about atoms, the smallest particles, but the first person to put it together into a more scientific manner was Dalton, and this was in the 1800s. And so we have Dalton's atomic theory. And so from these experiments, did Dalton come up with atomic theory? Lots of people came up with atomic theory without having the evidence, but how did he convince people to believe in atoms? Has anybody ever seen an atom? And so how do you convince people that atoms exist? If I gave you $100, could you convince me that atoms exist? What would you tell me to convince me? Because I'm very skeptical. I don't believe in atoms. I believed in atoms since middle school. Do you know why I believed in atoms since middle school? Because my middle school science teacher told me about atoms. And I believed them. But did they tell me any supporting observations or any evidence? No. And so if I were to convince you, I'd say, you should believe me because my middle school teacher told me, and therefore you should trust my middle school teacher. Would you? No. And so here, this is the difference. In this, he has supporting evidence. Now, in Dalton's time, this is in the 1800s. In the 1800s, has anybody seen an atom? In the 1800s, how hard do you think it was to convince people who have never seen an atom to believe in atoms? Pretty hard. So he must have had some convincing evidence. What was the convincing evidence? Well, you think burning this stuff, is that convincing enough? Well, it is actually, because there's one other thing here. The one other thing that theories must do is this. A hypothesis and theory must both be fundamental explanations. It's not explanation, it's a fundamental description. And so the fundamental description, observation here, the atoms are being rearranged. But a theory should do 2 things. One, a theory should be a fundamental description, and two, a theory should be able to predict new observations, etc. Laws. So I told you this is an empirical law, but we have two ways of generating laws. One way of generating laws is strictly from observation, therefore we call it empirical. Another way of generating a law is from theory. So we can use the theory to make a prediction. Nature should do this. And so the theory that was predicted is this. We have a couple of other laws that are important back in the old days. One law is the law of constant composition. If you have pure water in California and pure water in New York, are they going to have the same composition? Yeah, they're both going to have 2 hydrogens and 1 oxygen. Now, the other law is this. It's called the law of multiple proportions. So, for example, can I have 2.5 hydrogens and 1 oxygen? No. They have to combine in simple whole numbers. So hydrogen peroxide's 2 hydrogens, 2 oxygens, H2O2, correct? But nothing in between. So I can have H2O1, H2O2, but nothing in between there. So I can't have 1.5 oxygens unless I increase the ratio. And so that's the law. It's called the law of multiple proportions. And based on this, he was able to convince a lot of people of the atomic theory.
What does it say? Does it predict new?
New observations, laws, etc. So there's a huge difference. David Sinclair is looking for the elixir of life using the scientific method. The alchemists were looking for the elixir of life using magic. And so the transition was around Lavoisier. Does that make sense? All right, what time do we end?
4:25.
4:25. How did I get so far ahead? So, important things. The ultimate end is theory. If we understand the theory, then we understand everything because we should be able to predict things. So if you understood the theory of matter, then we could predict if an elixir of life should exist or not, correct? That kind of thing. But this makes it look like the ultimate end is the law. Is the law really the ultimate? We can use the law. For example, there's no problem. We could use the law to make predictions. So the law of conservation of mass, we can make lots of predictions based on that. But using that law, can we make predictions of new, unforeseen? So if we knew the law of conservation of mass, could we have predicted the law of multiple proportions? No, it's not the case. And so the law is kind of in the middle, and the hypothesis is before. So this is all kind of mixed up. And so that's one thing I don't like about this. This is correct, skepticism. This is how science polices itself. We don't need somebody to police science for us. You know, we don't need some kind of, what do they call it, fact checker or whatever else. Because all scientists are fact checkers, you know. And who makes the final decision is based on argument. Predicting, testing, revising. Revising, sometimes the theory, like Dalton's atomic theory, had to be revised. And the law of conservation of mass actually had to be revised because there were new observations that didn't conform to these laws and theory. But it was just modified slightly, so it wasn't completely revolutionized. All right, any questions on this? So just some of the features, observing. We don't propose a hypothesis right away. We try to get as much observations as possible and maybe some laws thrown in there and some patterns. We look for patterns and trends. So for example, take a look at all the observations there. When you look at all the observations there, somebody asked me, should I memorize that chart on the left? Do you want to memorize that thing? No, that's a lot of observations, but scientists aren't going to leave it at that. You know what scientists are going to do? They're going to look at that chart and then look for patterns and
Trends. That's what you want to do. Do you want to go inside the forest and memorize every single tree in the forest? No, you want to look for patterns and trends. And then if those patterns and trends are precise and reproducible, then you might come up with a law, you know? And so those are the types of things. In law, there's some patterns in there, for example, with water. And you call that the law of water. And then we start to think, what's a more fundamental description for that? And so my scientific method is organized a little differently than theirs, but please, for the test, use mine. And this is revising and then testing and then theory. And theory is a hypothesis that is tested and confirmed by experiments under varied conditions without contradiction. Conducting more experiments, but this doesn't have the most important thing for the theory. The most important thing for the theory is to be able to predict, you know, without having to observe. Okay, this is all mixed up for me, and so this is why I don't really like it. This is why chemistry is called the central science, because matter makes up the physical material of the universe. So this is chapter 1 here. I guess I will end a little bit early, but we're going to end with a quiz, actually. Now, the quizzes and the exams are a bit different. The exams are closed book, closed notes, and individual work. Anything else would be considered like cheating. But the quizzes are open book, open notes, and you can work with anybody you want. So you can work with your neighbor, your friends. Now, there's no prerequisite for this. So if you don't know the answer, that's okay, but maybe somebody else in your vicinity will know the answer. And that's okay to get the answer from them. Must have skipped something.